We'll start in 1 minute. Okay, today we'll cover the material in section 8.4, operations with radicals, where we add, subtract, and multiply. The first reminder of the next test, test 3, will be 1 week from today on Friday, March 26th. Later today, I'll send a test 3 review sheet. First, we talk about adding and subtracting radicals. Like radicals can be combined by adding and subtracting. So the concept of a like radical is similar to a like term, or like terms. Simplified radicals are called like radicals if their indexes, variable parts, and radicands are the same. So like radicals may have different numerical coefficients. Okay, so when we simplify by adding and or subtracting, we first want to make sure that the radicals are as simplified as they can be. In this first example, we have 11 times the square root of 3 minus 7 times the square root of 3. So we know that the square root of 3 cannot be simplified further, and the radicals are the same, and we are subtracting. So we can simplify by subtracting 11 times the square root of 3 minus 7 times the square root of 3 simplifies to 4 times the square root of 3. So it's a similar idea to combining like terms. For example, if we had 11x minus 7x, we know how to simplify that to 4x. Okay, in the next example, 5 times the square root of x plus 3 times the square root of x minus the square root of x. Each of the radicals is simplified as much as possible, and the radicals are the same, so we can combine by adding and subtracting. So 5 times the square root of x plus 3 times the square root of x. Up to here, we have 8 times the square root of x, and then we subtract 1 square root of x, and we end up with 7 times the square root of x. Okay, the next example, here we have 14y times the cubed root of 9x plus 11y times the cubed root of 9x. The cubed root of 9x cannot be simplified further because the largest factor of 9x that's a perfect cube is 1. And so the cubed roots are identical, but also note that on the outside we have the variable y that appears in both. So these are like terms or like radicals, and so they can be combined by adding. That means 14y times the cubed root of 9x plus 11y times the cubed root of 9x simplifies to 25y times the cubed root of 9x. And then the next example, 13 times mn times the fourth root of 7r minus 10 times m times n times the fourth root of 7r. The fourth root of 7r cannot be simplified further. Both terms have the fourth root of 7r, but they also have the factors m times n on the outside. So we can combine these like terms by subtracting. So that means 13 times mn times the fourth root of 7r minus 10 times m times n times the fourth root of 7r simplifies to 3 times m times n times the fourth root of 7r. Okay, a couple more examples. Here we have 19x squared times the fifth root of 12y to the third minus 3x squared times the fifth root of 12y to the third. The fifth root of 12y to the third cannot be simplified any further. Both terms have the fifth root of 12y to the third, but they also have x squared on the outside of the radical. And since we're subtracting, we can combine the like terms by subtracting. Okay, so 19x squared times the fifth root of 12y to the third minus 3x squared times the fifth root of 12y to the third simplifies to 16 times x squared times the fifth root of 12y to the third. All right, the next one. Negative 7 times a to the fourth times b to the fifth times the seventh root of 11c plus 10a to the fourth times b to the fifth times the seventh root of 11c. The seventh root of 11c cannot be simplified further. The terms are like terms, so we can combine by adding. So negative 7 a to the fourth b to the fifth times the seventh root of 11c plus 10a to the fourth b to the fifth times the seventh root of 11c simplifies to positive 3 times a to the fourth times b to the fifth times the seventh root of 11c. Okay, so remember, we can combine like radicals when adding and subtracting. So we want to make sure we distinguish the procedures between adding and subtracting with other operators. Okay, let's look at the next page. In the previous examples, all of the radicals were as simplified as they could be, but we won't always have radicals that are already simplified. So here it says simplify the radicals and then combine like radicals by adding or subtracting. Okay, in our first example, 2 times the square root of 75 minus 9 times the square root of 48. Both of those square roots can be simplified further, so we have to do that first. Okay, so 2 times the square root of 75, the largest factor of 75 that is a perfect square is 25. 25 times 3 is 75. So we'll rewrite this as 2 times the square root of 25 times the square root of 3. And then the other, we're subtracting 9 times the square root of 48. The largest factor of 48 that's a perfect square is 16. 16 times 3 is 48. So we're going to replace minus 9 times the square root of 48 with minus 9 times the square root of 16 times the square root of 3. Okay, in the next step, we simplify the two square roots of the perfect squares. 2 times the square root of 25 times the square root of 3 is 2 times 5 times the square root of 3. And then minus 9 times the square root of 16 times the square root of 3. That becomes minus 9 times 4 times the square root of 3. Okay, then 2 times 5 times the square root of 3 is 10 times the square root of 3. And we're subtracting 9 times 4 times the square root of 3, which becomes minus 36 times the square root of 3. We're subtracting like radicals. So 10 times the square root of 3 minus 36 times the square root of 3 simplifies to negative 26 times the square root of 3. And the next example, simplify the radicals if possible first, and then if there are like radicals that remain, then they can be combined by adding and subtracting. Okay, simplify the square root of 45. The largest factor of 45, that's a perfect square, is 9. 9 times 5 is 45. So we replace 2 times the square root of 45 with 2 times the square root of 9 times the square root of 5. The square root of 48 can be simplified. The largest factor of 48 that's a perfect square is 16. 16 times 3 is 48. So we replace 5 times the square root of 48 with 5 times the square root of 16 times the square root of 3. And then simplify the square root of 20. The largest factor of 20 that's a perfect square is 4. 4 times 5 is 20. So we replace minus 3 times the square root of 20 with minus 3 times the square root of 4 times the square root of 5. Simplify the square roots of the perfect squares. 2 times the square root of 9 times the square root of 5 is 2 times 3 times the square root of 5. And 5 times the square root of 16 times the square root of 3 becomes 5 times 4 times the square root of 3. And minus 3 times the square root of 4 times the square root of 5 becomes minus 3 times 2 times the square root of 5. Hey, then 2 times 3 times the square root of 5 is 6 times the square root of 5. And plus 5 times 4 times the square root of 3 is plus 20 times the square root of 3. And then minus 3 times 2 times the square root of 5 is minus 6 times the square root of 5. Notice that not all 3 are like radicals, but 2 of them are. So we can simplify 6 times the square root of 5 minus 6 times the square root of 5, which is 0. And so we end up with 20 times the square root of 3. Okay, the next level of difficulty. Here we have 4 times the square root of 18x y squared plus the square root of 8x y squared minus 5y times the square root of 50x. Each of those square roots can be simplified further. So we start with the one on the left. So inside the square root, we have 18xy to the second. The largest factor of 18 that's a perfect square is 9. 9 times 2 is 18. Y squared is a perfect square because the exponent is even. And x will have to stay behind inside the square root. Okay, so when we rewrite this, we can write it as 4 times the square root of 9 times the square root of y squared times the square root of the remaining factors, which are 2 times x. You can verify by multiplying the radicands to see if you're doing it correctly. So 9y to the second times 2x is the same as 18xy to the second. But we separated the square roots of the perfect square factors from the leftover factors. Okay, we'll do the same sort of thing with the next term, the square root of 8xy to the second. The largest factor of 8 that's a perfect square is 4. 4 times 2 is 8. Y squared is a perfect square. So we'll rewrite the middle term as plus the square root of 4 times the square root of y squared times the square root of 2x. And then check 4y to the second times 2x. That's the same as 8xy to the second. And then we have minus 5y times the square root of 50x. The largest factor of 50 that's a perfect square is 25. 25 times 2 is 50. So we can rewrite this as minus 5y times the square root of 25 times the square root of 2x. Okay, in the next step, simplify the square roots of the perfect squares. 4 times the square root of 9 times the square root of y squared times the square root of 2x. Well, we get 4 times 3 times y times the square root of 2x. In the middle term, the square root of 4 is 2, the square root of y squared is y, and then times the square root of 2x. And then minus 5y times 5, the square root of 25 is 5, times the square root of 2x. Okay, then simplify further. 4 times 3 times y times the square root of 2x is 12 times y times the square root of 2x. This middle term can't be simplified further, so plus 2y times the square root of 2x. And then minus 5y times 5 times the square root of 2x is minus 25y times the square root of 2x. Each of the 3 terms is like the other 2. So they are like terms, and they can be combined by adding and subtracting. So we have 12 of those terms plus 2 more. So up to here we have 14. And then we're subtracting 25 of the same. So we're left with negative 11 times y times the square root of 2x. That is our simplified result. And the next example involves a cube root. Okay, the cubed root of 16m. Now we want to find the largest factor of 18 that is a perfect cube. So 8 is a perfect cube. 2 to the third is a perfect cube. And 8 times 2 is 16. So we'll rewrite this as the cubed root of 8 times the cubed root of 2m. And then verify 8 times 2m is 16m. Okay, then the middle term, inside the cube root, we have 54m. The largest factor of 54 that's a perfect cube is 27. 3 to the third is 27. So and 27 times 2 is 54. So we rewrite this as 5 times the cube root of 27 times the cube root of 2m. Okay, then the next cube root, we have the cube root of 40m. The largest factor of 40 that's a perfect cube is 8. 8 times 5 is 40. So we'll rewrite the third term as 2 times the cube root of 8 times the cube root of 5m. The cubed root of 8 is 2 because 2 to the third is 8. So we get 2 times the cubed root of 2m. And in the middle term, the cubed root of 27 is 3 because 3 to the third is 27. So we have plus 5 times 3 times the cubed root of 2m. And in the third term on the right, the cube root of 8 is 2, so we have 2 times 2 times the cube root of 5m. Okay, a couple of more steps. 2 times the cube root of 2m plus 15 times the cubed root of 2m plus 4 times the cube root of 5m. Only 2 of the terms are like terms, so we combine the like terms by adding. So 2 times the cube root of 2m plus 15 times the cube root of 2m is 17 times the cube root of 2m. And then we add 4 times the cube root of 5m. And that is as far as we can simplify this, because the remaining 2 radicals are not like radicals. Okay, the next example, the third root, or cube root of 54n to the third plus 5n times the cube root of 54 minus 2 times the cube root of 16n to the third. Okay, starting on the left, the largest factor of 54 that's a perfect cube is 27. 27 times 2 is 54. N to the third is a perfect cube because the exponent 3 is a multiple of 3, so it's a perfect cube. So we'll rewrite the first term as the cubed root of 27 times the cubed root of n to the third times the cubed root of 2. That's the leftover factor inside the radical. Okay, then the middle term plus 5n times the cubed root of 54. So once again, the largest factor of 54, that's a perfect cube, is 27. So we'll rewrite the middle term as plus 5n times the cubed root of 27 times the cube root of 2. And then finally, the third term, we're subtracting 2 times the cube root of 16n to the third. The largest factor of 16, that's a perfect cube, is 8. And n to the third is a perfect cube because the exponent is a multiple of 3. So we have minus 2 times the cube root of 8 times the cube root of n to the third times the cube root of 2. Okay, in the next line, we'll simplify the cube roots of the perfect cubes. The cube root of 27 is 3. The cube root of n to the third is n to the first, and then 3n times the cube root of 2. And then in the middle term, 5n times the cube root of 27 times the cube root of 2. The cube root of 27 is 3, so we have plus 5n times 3 times the cube root of 2. And then on the right, minus 2 times the cube root of 8 times the cube root of n to the third times the cube root of 2. So we have minus 2 times 2, because the cube root of 8 is 2, times n. The cube root of n to the third is n, and then times the cube root of 2. The three terms are like terms. They have the exact same cubed root of 2, and they also have one factor of n outside of the radicals. So we'll simplify the three terms. This one is already simplified, 3n times the cube root of 2, and then 5n times 3 times the cube root of 2. That simplifies to 15n times the cube root of 2. And then minus 2 times n times the cube root of 2. That becomes minus 4 times n times the cube root of 2. And finally, we can combine all three into one. So we're adding 3 of those terms plus 15 more. So up to here we have 18. And then we're subtracting 4. So we get a total of 14 times n times the cube root of 2. Okay, that concludes our sample of adding and subtracting with like radicals. So now we'll look at some multiplication. So make sure you distinguish between multiplying and adding and subtracting. So when we multiply radicals, we will apply the product property of radicals, which we have seen, but now we're going to use it in the other direction. The product property of radicals, let n be a positive integer. If the nth root of a and the nth root of b are real numbers, then we can multiply the nth root of a times the nth root of b and write it as a single nth root of a times b. We applied this property in reverse when we were simplifying radicals. Okay, but now we're going to multiply radicals and simplify. There's more than one way to go about it, but in my opinion, there's a more efficient way to multiply radicals that have the same indexes. So here we want to multiply the square root of 12x to the third y to the second by the square root of 3x to the fifth y. So in my opinion, applying this property directly, write this as a single square root and multiply the radicands. So this property says we can write the square root of 12x to the third y to the second times the square root of 3x to the fifth y. We can write that as a single square root if we just multiply the radicands, 12x to the third y to the second times 3x to the fifth y. And then inside the square root, simplify the product. We can always rearrange the factors if you want. Or we can say, well, we know that 12 times 3 is 36 times x to the third times x to the fifth is x to the eighth. And then times y to the second times y is y to the third. Okay, then after you've multiplied both radicals and simplified the radicand, then just focus on simplifying the single square root. So now we're working on something that we already talked about. We want to simplify the square root of 36 times x to the eighth times y to the third. So we note that 36 is a perfect square. X to the eighth is a perfect square because the exponent is even. Y to the third is not a perfect square, but the largest factor of y to the third that is a perfect square is y to the second. Okay, so we'll just write down a couple more steps. We can think of this as the square root of 36 times the square root of x to the eighth times the square root of y to the second times the square root of y. And then simplify the square roots of the perfect squares. The square root of 36 is 6. The square root of x to the eighth is x to the fourth. And the square root of y to the second is y. And then we also include the square root of y as a factor. Okay, that's the simplified result. Okay, the next one, we're multiplying two cube roots. The cube root of 4x times the cube root of 2x to the second. Okay, if we just multiply, write this as a single cube root and multiply the radicands. So inside the cube root, we have 4x times 2x to the second. And then inside the radical, we simplify the product. 4x times 2x squared is 8x to the third. And then we focus on simplifying the cube root of 8x to the third. Well, we know that 8 is a perfect cube because 2 to the third is 8. And we know that x to the third is a perfect cube because the exponent is a multiple of 3. So we can write down the simplified answer immediately. The cubed root of 8 is 2. The cubed root of x to the third is x. That means x to the first, but we just write 2x. Okay, the next one involves a product of two fifth roots. The fifth root of 2x squared y times the fifth root of 3x to the third y to the second. With a little bit of practice, we can write down fewer terms. It's always important to be able to show your work, but we don't have to show every single thing that goes on. So on this one, we could just write a single fifth root, and then we can visualize what the product of this radicand with that radicand will be. So 2 times 3 is 6. X to the second times x to the third is x to the fifth, because we're adding the exponents, x to the second times x to the third. And then y to the first times y to the second is y to the third. Okay, now we just focus on simplifying the fifth root of 6 times x to the fifth times y to the third. The largest factor of 6 that is a perfect fifth power is 1. So in other words, we can't simplify the fifth root of 6 any further. The largest factor of x to the fifth that is a perfect fifth power is x to the fifth, because the exponent is a multiple of 5. And the largest factor of y to the third that's a perfect fifth power is 1. So in other words, the fifth root of y to the third cannot be simplified further. So we can rewrite this as the fifth root of x to the fifth times the fifth root of 6y to the third. The fifth root of x to the fifth is just x to the first, or x. And so our final answer is x times the fifth root of 6y to the third. Okay, and the next one, we have the square root of 5x to the seventh y to the fourth times 45 x to the ninth times y to the third. So let's just write a single square root. And let's, in our heads, without writing anything down, let's find the product of 5x to the seventh y to the fourth times 45x to the ninth y to the third. So 5 times 45 is 225. X to the seventh times x to the ninth is x to the 16th. We add the exponents. Y to the fourth times y to the third is y to the seventh. Hey, the largest factor of 225 that's a perfect square is 225. In other words, 225 is a perfect square. 15 to the second is 225. X to the 16th is a perfect square because the exponent 16 is even. And the largest factor of y to the seventh that is a perfect square is y to the sixth. Y to the sixth times y. Okay, so the perfect square factors are 225. So we can write the square root of 225 times the square root of x to the 16th. times the square root of y to the sixth, and times the square root of y. The square root of 225 is 15. The square root of x to the 16th is x to the 8th. Remember, the index of the index of a square root is 2. So when simplifying the square root of x to the 16th, it's x to the 16 divided by 2, or x to the 8th. And similarly, the square root of y to the 6th is y to the 3rd. And then we also have a square root of y. So this is our final result on that one. Okay, the next one, we have a product of 2 fourth roots. The fourth root of 2x to the 5th y to the 3rd times the fourth root of 8x to the 3rd y. So we'll write it as a single fourth root and multiply the radicands. So 2x to the 5th y to the 3rd times 8x to the 3rd y is 16x to the 8th y to the 4th. Inside the fourth root, we look for largest factors that are perfect fourth powers. 16 is a perfect fourth power because 2 to the 4th is 16. X to the 8th is a perfect fourth power because 8 is a multiple of 4. And y to the 4th is a perfect fourth power because 4 is a multiple of 4. So we can simplify this directly. The fourth root of 16 is 2. The fourth root of x to the 8th is x to the 2nd because the exponent 8 divided by the index 4 is 2. And then we also have y to the 1st, or the fourth root of y to the 4th is y. So that is our simplified answer. Okay, next we have the cube root of 3x to the 5th y to the 3rd times the cube root of 72x to the 7th y to the 6th. So let's write a single cube root, and let's multiply the radicands. 3 times 72 is 216. X to the 5th times x to the 7th is x to the 12th. We're adding the exponents. 5 plus 7 is 12. And then times y to the 3 plus 6, or y to the 9th. Now, this is kind of nice because each of the factors inside the cube root is a perfect cube. The cube root of 216 is 6, because 6 to the 3rd is 216. The cube root of x to the 12th is x to the 12 divided by 3, or x to the 4th. And the cube root of y to the 9th is y to the 9 divided by 3, or y to the 3rd. So we get a nice result on that one. Okay, let's look at the next page. Now we're going to multiply the following binomial-like factors and simplify. So here we have, in parentheses, the square root of 7 plus 3 times the square root of 2 minus 5. Okay, so just like you would multiply binomials, we have the square root of 7 times the square root of 2, and then minus the square root of 7 times 5. We can write that as minus 5 times the square root of 7. And then plus 3 times the square root of 2. And then minus 3 times 5 is minus 15. And the only thing that can be simplified is the square root of 7 times the square root of 2, which is the square root of 14, because 7 times 2 is 14. And nothing else, there are no like radicals or like terms. So we write the square root of 14 minus 5 times the square root of 7 plus 3 times the square root of 2 minus 15. So that is as simplified as it can be. Okay, in the next example, a couple of binomial-like terms. So 4 times the square root of 3 times the square root of 3, and then 4 times, we're adding 4 times the square root of 3 times the square root of 5. So plus 4 times the square root of 3 times the square root of 5. And then plus the square root of 5 times the square root of 3. And finally, plus the square root of 5 times the square root of 5. Okay, 4 times the square root of 3 times the square root of 3. Notice that the square root of 3 times the square root of 3 is just 3. So we get 4 times 3, and then plus 4 times the square root of 3 times the square root of 5 is plus 4 times the square root of 15. And then we're adding the square root of 5 times the square root of 3, which is plus the square root of 15. And then the square root of 5 times the square root of 5 simplifies to 5. So a couple of more steps. 4 times 3 is 12. The two middle terms are like radicals. 4 times the square root of 15 plus the square root of 15 is plus 5 times the square root of 15. And then finally, we can combine the 12 plus 5, so we get 17 plus 5 times the square root of 15. And that is as far as we can simplify that. Okay, so just a note, just as an example, 4 times the square root of 3 times the square root of 3 is the square root of 3 times 3. 3 times 3 is 9, so it's 4 times the square root of 9, but the square root of 9 is 3, so we get 4 times 3, 12. Or you can just remember the square root of a number multiplied by the square root of the same number is just the number. Okay, and the next one, 3 times the square root of x times 4 times the square root of x. Okay, I'll write it out. 3 times the square root of x times 4 times the square root of x. And then minus 3 times the square root of x times 6 times the square root of y. And then plus the square root of y times the 4 times the square root of x. I'll write it as plus 4 times the square root of x times the square root of y. And then finally minus square root of y times 6 times the square root of y. So minus 6 times the square root of y times the square root of y. So this first product, 3 times the square root of x times 4 times the square root of x. 3 times 4 is 12. And the square root of x times the square root of x is the square root of x squared, which is just x. So this simplifies to 12x. And then the next term, we can write minus 18 times the square root of x times y. And then plus 4 times the square root of xy. And then finally minus 6 times y, because the square root of y times the square root of y is the square root of y squared, which is just y. And there's just one step left. The two middle terms have like terms. So we get 12x minus 14 times the square root of xy minus 6y. Okay, we can at least start the next one. 6 times the cubed root of x times the cubed root of x. 6 times the cubed root of x times the cubed root of x. And then plus 6 times the cubed root of x times 2. We can go ahead and write plus 12 times the cubed root of x. And then minus 5 times the cubed root of x, and then minus 5 times 2, or minus 10. So on this one, 6 times the cubed root of x times the cubed root of x, this will just be 6 times the cubed root of x to the second. The next two terms are like terms. Those add up to 7 times the cubed root of the cubed root of x, and then minus 10. Okay, so that is as far as we can simplify that one. Okay, we're out of time, so go ahead and sign in for attendance. How was that? Did that seem to all make sense?
Thank you.
Yeah.